Can I have your attention? Now, I'm distributing the notes that we are going to use today. And while you are picking it up, still we have almost half of you didn't get it yet. Let me give a few announcements. One of them I will explain a little bit later. Tomorrow you're going to have a quiz. Tomorrow and on Friday you're going to have a quiz in the sections. And another thing is about the term papers. The first requirement of the term paper that you have submitted will be available for you to pick up on Monday. So you need to go to the assistants, to the course assistants, to pick them up. They are still being checked. I am checking it personally myself, so it is taking some time. And I will also give some additional information on how to proceed later on. There are certain common mistakes that I see, so I will write something, but be prepared to go to the assistants on Monday at the office hour so that you can pick that up, where you are going to see a number of comments written on the paper that you submitted. Okay, and do we now all have, do we now have a copy of the course notes? Let's see. You don't have it yet. Okay. You have. Okay. Do you all have one copy? Okay. Sizlerin boyu uzun. Şunu şöyle bir itebilir misiniz? Şunu. Şu tarafa doğru, içeri doğru itebilir misiniz? Şunu benim. Şöyle çevirelim. Tamam. Okay. Okay. That might be the reason for the noise, actually. That's what I felt. We'll see. We're trying. Otherwise, I'll take my microphone off. Okay. Now, today what I will do is I will start by reviewing what we did last week. Because what we did last week turns out to be something which is very important in the sense that it describes a lot of things that you should expect and at the same time not expect from your future courses. Okay, I shouldn't be moving at all. Just talk, don't move. That might be the solution, yeah. Okay, so let me go over the notes of last week. This is very critical because this is basically what we are trying to do in this course in 102. I'm not trying to teach anything about networks. We are seeing certain things on and off. So it is not valuable unless you have a coherent theory that will wrap it up, okay? So we are not aiming to do that in this course, of course. My aim is simply to show you that there exist certain methods. The methods have some assumptions around it. But moreover, those methods are applied to certain structures which we can utilize by looking at the real world and bringing those structures as the problem statement into mathematical forms, and we can solve it. That's the idea that I want to convey. Now, we have seen three different network problems: shortest path, TSP, traveling salesman problem. Okay, let's try once more. It might be better to speak from here. I don't know what's happening, but. Okay, and so we have three different problems that we have seen: shortest path, TSP, and assignment. And if you remember, shortest path problem is very simple to specify. Solution turns out to be difficult if we didn't know Dijkstra's algorithm. And TSP, on the other hand, is even simpler to describe. But it turns out that we don't have any algorithm that will solve it in a reasonable time. if the number of nodes is very large. The assignment problem is a little bit more difficult to explain because you need to talk about workers, tasks, and have some kind of a matching. And it turns out that we have an algorithm that will solve that specific problem. Okay, so what are the things that we should talk about these models? These are all network models. Now, first of all, they are examples of some representation of real issues that we can do mathematically. We always have a problem that is associated with shortest path, TSP, or assignment. So those are the things that we easily could give examples of, but they are examples of real-life situations which are described in that respect, in that manner. So this means that, actually, our first role as industrial engineers is to be able to make that representation. But on the other hand, you need to know a little bit about the assignment problem or TSP problem before you can actually make that representation, because by analogy, you are going to derive that representation and solve a certain problem. Okay, so this is one of the objectives. Now, the description of the problems might be relatively easy. The solution, we don't know, actually. The problems that we have here are easy to solve. Of course, we didn't talk about all possible extensions of these problems. I tried to ask some of them in the homework, some of them in the exam, and sometimes you think that it's very straightforward to solve it, to solve the extension as well, but we're going to see that actually it's not actually the case. So we have good examples for that. The question in the exam, for example, is a very good example to that. Okay. So this side is cursed. Okay. So curse. Okay. Now, so if I now make the explanation a little bit more technical, okay, I'm going to introduce a notion called NP-hard. Now, what we mean by NP-hard, I don't want you to understand it, but you need to hear about that. And basically, it means non-polynomial hard problems. And the explanation, the definition of it is very simple. Number of operations. Remember the discussion that we had about number of operations? Each time that you make a comparison or you make an addition, actually you perform some operations. Now, if the number of operations required to solve a problem by a certain algorithm is not polynomial, but, for example, is n factorial with respect to the number of nodes, we call those type of algorithms as non-polynomial. Now, why is this that important? You are probably not going to hear this word unless you take a specific course in the 4th year, which is an elective course. You might hear about that in 303 probably a few times. We are not going to do anything, but this means that, remember, if we have a very large problem where number of nodes is very large, we won't be able to solve this problem with the known algorithms that we have in a reasonable time. So if the problem description is simple, don't be deceived by the fact that I can enumerate all the possible solutions and get the optimal solution. You won't be able to do that in most of the real-life examples. Most of the real-life cases belong to problem sets which are called NP-hard. So what we need to solve those problems actually is two things. One thing is we can eliminate certain parts of that real-life problem which are not very relevant. Okay? That's called modeling. In other words, when you are converting real-life problem to, let's say, a shortest path problem, there might be some impurities that you are not going to consider because you know that they will happen, but they will rarely happen. Okay? So the certain things can be left out of the picture. Now, this is number one simplification, of course. But if you leave those as is, and then things are going to be very complicated. Humans, in general, when you ask a certain problem to the person who is dealing with that problem in real life, let's say a manager of some kind, will have the tendency of exaggerating the type of problem he or she is getting. In other words, they will always talk about those trivial, but I shouldn't say trivial, but those extreme cases and say that, well, this problem is very difficult because we have those extreme cases. But in general, you write down what are the chances of having an extreme case. And in most of the problems, you're going to see in real life that those extreme cases are really extreme. In other words, when you are trying to solve a problem in general form, you may leave those extremities aside. Of course, you might need a B plan if you encounter one of those. But that's the B plan. For the bulk of the problem, you may use the approaches that you already will learn in other courses. So this is what we call modeling. Modeling is an art in that sense because what you do is you understand the capabilities that you have with respect to solving a problem. And in order to fit the reality to those capabilities, you may need to do some reductions. So this is actually what we call reductionism. That's the basic rule of engineering. Let me give an example from another engineering field, because I think it's easier to understand. Let's say that we are dealing with the electricity distribution problem. Now, what you do is you distribute electricity in high voltage in between cities. Now, of course, what happens is that you assume that the world is not going to have an electromagnetic field of a certain kind in order for you to be able to do that. Now, in 99.99% of the time, you are not going to have an observed electromagnetic field around the world. Now, what happens if there is a meteor getting close to the world? Okay, if it is approaching the world, then you might have a lot of different problems coming out. Of course, you need to have a B plan. So what it means is that the current distribution system has its own limitations. So your approach will have its own limitations as well. Now, in order to set those limitations, you need to basically know about the methods, the capabilities of the methods, and the original problem that you are trying to solve. So to convert those two things together and come up with a solution requires some kind of a modeling, which is the art part of the modeling. Now, we won't be able to teach that through some common examples. We might give you some common examples in some other courses, but it turns out that with the real-life examples that you are going to see in your projects and other courses, in most of the courses, you're going to have a project, and there will be a project course. You might be able to deal with that problem and learn about that. But that's the part that is going to rely on you. Okay? So this is important to understand. And it turns out that this NP hardness is one of the curses that we have in the type of problems that we want to solve. Of course, there are certain problems that we don't have this issue. We can always solve those problems in the best possible way. Now, what happens if we cannot simplify the problem? We cannot reduce the problem. We have to take it as is because those are not rare events, but those occur all the time. So we have to include that in the problem. In that case, basically the only thing that we can use will be heuristics. So we are not going to have any guarantee of optimality. If lucky, we're going to get bounds, and we're going to use those bounds as benchmark and try to understand the quality of the solution that we have. So in most of the courses, you're going to learn about heuristics, okay, of very large-sized problems that we cannot solve for optimality under reasonable conditions. Okay. Now, what are the properties of heuristics? Heuristics should be easier to apply. In other words, we shouldn't have this curse of computation on those heuristics. Of course, heuristics should be based on some logic. You cannot say that this is the way that I want it to be. Okay? We're talking about an engineering field, so it should have some kind of logic. Now, usually, the way that we look at that logic, as you are going to see in the further courses, is actually very simple. We take a simple case. The solution, the optimal solution of that simple case is going to give you some kind of a logic. So in a lot of courses, you're going to see simpler versions of real problems where you can attain the optimal solution. You're going to learn that. That will be the basis, the intuition that you are going to learn. So memorizing those methods are not going to give you anything. You have to understand the intuition behind those methods. This is what we tried to do in the optimizing algorithms that we have seen up to this point. So that's the reason why we dealt with those type of issues in this course. But that will be something that you're going to see over and over again in the other courses. Now, finally, we have seen two types of heuristics. Heuristic number one is called actually a construction heuristic. So what you do is you construct a solution. At each step, you construct part of the solution. And eventually, you come up with the solution. For example, Dijkstra's algorithm is actually a constructive algorithm. It constructs the solution from some point in time. It starts with none, with a single node, and it adds up nodes as you proceed. Now, on the other hand, you can have improvement heuristics, like remember homework number 1, or the question that we had in the homework number 1. And basically, you have a solution. You do interchange, triangle insertion. You do different types of interchange, and you obtain a better solution. That's called improvement. Now, this improvement logic is much closer to what we do as IEs. So, but you need to have a solution for that to begin with. In real-life examples, you always have a solution because there's a current way of doing things. So, but whenever you are establishing a heuristic, you have to understand that there are two aspects of that: to find a solution, a feasible solution, and then next thing is to improve that solution. Now, in general, we're going to have both aspects in the heuristics that you see in different courses. This is misspelled. I'm sorry, available. It should be available. OK. Now, what is the implication of all of these for the courses that you are going to see in the IE curriculum? Now, there are two implications. Number one, you are going to see some theory in the sense that we're going to define a lot of simple problems. For example, in production planning, you're going to see a lot of simple scheduling problems. In some other courses, you're going to see a lot of problems that are simple, has a lot of restrictions and so on. But in those problems, we will be able to get the optimal solution. So this is the learning phase. We're going to learn what are the properties of that optimal solution in that circumstance. But that will give us intuition about the things that we are solving. In some other courses, we're going to learn some computational tools. Okay? Whenever we have a hard problem, okay, we are going to see that that hard problem can be solved by some numerical techniques. So in some courses, you're going to learn those numerical techniques so that you will be able to come up with a solution to a relatively hard problem that you cannot obtain by an algorithm that moves from step 1 to step 10. Okay? So this is something else that we're going to see. Thirdly, whenever we start taking some courses on different functions of industrial engineering, like quality control, production planning, rather than the methods that we use, like simulation, operations research models, stochastic models, and so on, when we come to functions, you're going to see that we are going to talk about a large number of heuristic solutions. Those are going to be relevant to the problems, to the real-life problems. Now, in this course, what I am doing is I am embracing all of these methods. I am trying to do that together so that we have an understanding of the type of things that we're going to have in the future. But in some courses, you are not going to have that. Some courses will be purely solving a certain problem. Or another course would be simply purely solving optimally a certain class of problems. So you have to understand that different courses are going to demand different things, but it's like Lego. You're going to bring all the pieces together in the 4th year, hopefully, and understand that these are important. So my role here in 102 is not to teach you to solve, let's say, the shortest path problem, although, I mean, I will be doing some exercises. That's something else. I'm calling it as exercises. But my main emphasis in 102 is to teach you the fact that you're going to see all of these in the future, not necessarily in a coherent way, but eventually you need to bring all of them together, because this is the logic of having this course earlier in your curriculum. Any questions on this? So we started from networks, but it actually tells you a number of things that we have in the curriculum. Actually, it turns out that we will see other techniques as well, some glimpse of other techniques, and I can say the same thing for those techniques as well. So I'm not going to repeat that probably, but it is going to apply to those other techniques as well. Okay, questions? So if I were you, I would keep in mind this lecture. And believe me, after 3-4 years, before you graduate, I will probably ask you, well, or the department is going to ask you questions about, before you leave this department in 3 years' time, about this specific discussion that I had about different types of methods and so on, in a more abstract way. You will probably have those type of questions coming in. Okay, and that's that, because this is the purpose of 102, and we want to check whether 102 is really doing that job correctly. So trust me, if you come back to the videos will be available all the time, even if I am not, even if somebody else is going to teach the course. Videos will always be available, so you can always come back and check this lecture specifically, because I think it is important for you to remember this over and over again. Okay, questions again? Comments? Okay. Now, this is the topic of the quiz that we're going to have this week. Now, I will be talking about performance measuring and performance measure ideas throughout today's lecture. And what we will do is, tomorrow, we're going to have a quiz in the 2nd hour. And in the 1st hour, we're going to have an example that will be very similar to the quiz. And I will distribute the example that I'm going to use via email after the lecture. Okay? Now, so what we are doing is simply the following. I will give the description of a case, which is basically a description of the process tomorrow. It will be short, 2 paragraphs at most. And then you will be asked to write performance measures that may fit to the situation described. Of course, every section will get a different case. And first part, I will ask if you have any questions. I will let you read first and ask if you have any questions about certain words, anything that you didn't understand. So we're going to discuss it in the classroom. And then what you are expected is you are expected to understand the process and define related performance measures and be ready to comment on how they can be measured. And these are the things that we're going to learn today. You're going to have open notes, open reading material for tomorrow. So that will give you an encouragement of reading it ahead of time, so that if you want to remember something, you know where to find it. You're going to have time pressure, of course. You will probably do it in 20-25 minutes. Once we discuss everything, the time that's left to you is 20-25 minutes. So you won't be able to read your notes at that time. So this gives you sort of like, if you look at the notes half an hour before going to the exam, I think you would remember which part is what. Okay. So let's now start the definitions with the definitions of performance measures. So I think Basically, I am using 2 references here. But as you are going to see, we're going to talk about, well, I will mention 5 references in total. And 4 of them are already, they are already available in in the website. The 5th one is a book at the library. Though that's not very important, but if you are interested, it's a very good reference, and that's the reason why I'm going to give it. Now, there are 2 fundamental dimensions of performance. Now, we all understand the word performance. Now, what we mean by the word performance is that you are designing something in the hope that it is going to solve certain problems. So, for example, we designed Dijkstra's algorithm in order to make sure that to find the distance, we can find the minimum distance between 2 nodes. Okay? Now, let's say that we are not mathematicians, so we couldn't prove that it was the optimal. But basically, that's something that we design. Or we design a queuing system for the new cafeteria. How many of you have been to the new cafeteria? I think it's nice. It will be much better during summer because we will be able to go out. I think it's nice and clean and it's not smelling, which is the most important part. So we have to enjoy this period because I'm sure that like in 2 years' time it will start smelling like the other cafeterias around the world. And so we have designed that cafeteria, but there is this queuing problem. What do we mean by queuing problem? Let's say at 12:25, if you go there, there are a lot of people waiting in the line. And we're not sure whether the number of servers that we have in the system, the number of lines, is sufficient. Can we put another cafeteria line somewhere else in the whole structure so that we will increase the processing? Or can we have some better ways of arranging the food so that it will flow much better? We still don't know that because it's a system which is designed. Okay? It will live and we're going to learn certain things out of it. Of course, while it is designed, everybody thought about certain parameters and so on, and the design was done accordingly by the professionals. Okay? But we're going to live through the system and see whether we're going to have a lot of problems. But what we need to do is we need to understand the performance of the current system. So that's what we mean by performance. Now, it turns out that there are 2 fundamental dimensions of the performance. The first one is called effectiveness, and the second one is called efficiency. The first one is basically the extent that the requirements are met. Now, of course, when you are designing a system like this, there are certain requirements which are given to the professionals. And what are those requirements? Very simply, those requirements are, in the peak hour, we shouldn't expect a student to wait, or somebody who is going to eat there to wait, let's say, more than 15 minutes. That's the requirement. So the chances of having such an event should be very small. So measure of effectiveness with respect to performance means that are these requirements which are set by the university ahead of time met? So we need to figure out whether these are met or not. Okay? Now, we shouldn't expect a system that will not allow anybody waiting. Am I right? That will be probably something that probably you will design for the 22nd century. Okay? So you go there, you clap your hands, the food is going to be available. Okay? If you are content with a little pill, okay, that might be possible actually. When you do this, you're going to have your soup pill and meat pill and the dessert pill coming in, very simply. And by doing this, you already paid that money immediately. Okay? So, but that's a dream, of course. But we are going towards those type of systems. That's the objective. But eventually, you are going to wait. And we all accept the fact that we are going to wait for some time. But the amount of waiting that we have, which are set by the requirements, are they met by the current system? These are called the measure of effectiveness. Now, on the other hand, the second part is efficiency. And this is not usually given in the design, but we want to make sure that we are going to economically use the resource so that the money that we spend for the whole building is going to be meaningful. But there are other resources as well. For example, cashiers. We are going to pay them some salary. Are they sufficiently utilized? Or the people behind the line who are preparing the food and bringing it in. We already decided to have 10 people per line, but is it too much? Is it too small? Economically, so efficiency is something related to the economics, to the money related to that. And effectiveness is your expectations with respect to service. So these are the two fundamental types of performance that we are going to have. Now, we have an example there. Remember in homework number 1, we had these nurses that we used for blood drives. Okay. So if we are looking for a measure of effectiveness, can we meet the requirements set by the high health standards by the way that we designed the process of blood taking? There are certain health standards which requires you to check, for example, every blood before you take it. Okay, are we allowing in our process, allowing for those type of standards to be fulfilled? With respect to efficiency, are we using the nurse resource economically? Or are we using the individual blood trucks economically? Or we're just putting it there and they are only taking 2 people's blood and idle for the rest of the time in that day. Okay? So these are the 2 different things that we are thinking of. Okay. Now, let me go to my spot again. Okay, so it's very hard for me not to walk, believe me. I'm dying to walk. So I will just throw this away and start walking. Okay, now, what is performance measurement? Again, this is definition. Process of quantifying the efficiency and or effectiveness of an action. So you set up a certain process. You show it with a chart. Then we are going to measure it by performance measurement with respect to efficiency and effectiveness measures that we are going to define. Okay? Unless we do that, what we do is not going to be analytical. What can you say about a process? You can say probably it looks very nice. It seems to be nice. I want to write a term paper on it. Okay? But what we are after is we are after a serious evaluation just to make sure that we don't repeat the mistakes and we improve the system. So in order to be able to improve the system, we have to have some measures so that we're going to improve looking at those measures. So performance measure, on the other hand, is a metric or a measure used to quantify the efficiency and or effectiveness of an action. So measure means that we have some kind of a quantification. Quantification is not necessarily a number. It can be a rank, like the best you can have, like, for example, number 1, number 2, number 3. Or it can be a specific number, or it might be a grouping, or it might be a composite of these 3. And we're going to see examples of that later on. But at least it is something that you can quantify. Next time that you go there, you will be able to measure something which is comparable. That's the idea. A measure is something that you will pick up, learn at some point in time. Next time that you do that, it should be something comparable to that. Okay? So for example, when we are managing certain countries, the economics have some specific measures. For example, one measure that all the countries around the world looks at as a success of a certain government is the per capita income. Okay? And that is computed in a certain way. The computation should not be different from one country to the other. There are certain standards, of course. And you have to make sure that you obey those standards when you are doing the computation. Another one is the Human Development Index. How many of you have heard about the Human Development Index? Okay. So basically what Human Development Index is a composite measure that is made up of a number of things, like education level in a country, economics of a country, or judiciary in a certain country. And those composite structures are brought together by the use of an index. Okay? And that index is actually called Human Development Index. And countries are sort of ranked according to that index, which is commonly accepted by all the countries. Of course, the exact value doesn't mean anything, but the relative values are what is important. Another one is the inflation rate. Do you know how the inflation rate is computed? Well, there is a certain basket of products that is accepted to be the norm, and the price change of that basket of products are used to calculate the inflation rate. So, for example, in the basket, you have to make sure that you have things that are relevant rather than non-relevant things. For example, the price of a telephone turns out to be very important in these years. Of course, 20 years ago in the basket, we didn't have that. Okay? So by using the basket consistently, you can compute the inflation rate of a certain country. It's an index, actually. It's not a single number. It's a composite number it's a composite measure that we compute by bringing different numbers together. So this is basically what we mean by performance measure. Now, do you have any suggestions with the previous example? For example, remember what was the previous example? The example was nurses. For example, what is a suitable performance measure for the nurse example that we had in the homework? Okay, let's, for example, think about the efficiency of the nurse. So give me a measure which is going to measure the efficiency of a nurse. Okay, this will be the type of questions that you're going to get tomorrow. Okay? Because you're going to have the text in front of you, and you have to come up with a performance measure for the efficiency of the nurse. Very simple. You're going to look at the time for which, for example, the nurse will be idle. Okay? Of course, we are expecting that the nurse should be idle for at least 20% of the time, because we're talking about a human. She's not going, or he's not going to be a robot. Okay? But basically, that's a good indicator of the amount of work that that person is doing. For example, the amount of time that's spent for waiting a patient might be another indication of the efficiency. Now, why am I taking this as efficiency factor? Because we are paying the nurse a certain amount of time, amount of money, and basically we are trying to figure out whether we are utilizing the nurse efficiently or not. Okay, so there are measures that you're going to see other things as well, but basically this is what we are aiming. Okay. Now, why do we measure? Now, of course, we now understand why we are measuring, but let's bring in some more classification so that we understand the purposes of measuring. Now, the second paper, Ben, summarizes this in a very nice way. There are a number of reasons, but these three reasons are the reasons that we should put a lot of emphasis for, because those are the very relevant reasons that we are using it for performance measuring. Number one is to evaluate. We want to find values to judge the worth of something. For example, is this operation efficient? Well, it is 70% efficient. That's a value that you assign to that operation. What is the total time that it takes to do certain things? Well, I have computed this, and it takes 2 hours. 2 hours is a definitive value. So to judge whether it is good or not, you need to have some kind of a value in front of you. Now, of course, real decision making is not going to utilize only one performance measure value. There will be a number of performance measure values that will be used concurrently to make good decisions. But at least we know what we are computing. This is the number one reason. Number two, we use it for control purposes. Okay? For example, if we are talking about success of a certain government, we look at the inflation rate. This is what the Central Bank of Turkey is doing. They are checking the inflation rate. They are looking at the other, there are 3 or 4 different measures that they have. They basically want to do it in order to control the stability of the environment. Now, if they see that one of them is coming out of control, they take some precautions. Okay? So to control, we actually use performance measurement. And finally, we use performance measurement to improve, of course. Think about Kaizen example. Okay? The time to finish everything was 4 minutes, but with the improvements, it turned out to be 2.5 minutes. So how are you going to show your improvement? You need to use a measure, which in that case is time, in order to show that. Similarly, in the traveling salesman problem that we solved in the classroom, we wanted to improve the algorithm so that the total time that it takes, or the total cost that it takes, is now a little bit lower than what it was before. So this is for improvement, and for those purposes, we use performance measures. Now, Dijkstra's algorithm, for example, is using a certain performance measure. When you are utilizing it in Dijkstra's algorithm, we don't need to know what it is. But if you are applying Dijkstra's algorithm to a real case, that becomes very important, because those are the things that you are going to talk and show how you have improved different things. Okay, any questions? Okay, let's take a break, and I want you to be back in 13 minutes.